So hey guys, welcome back. Today we will be learning neural network. In our previous video, we studied gradient descent and we saw how we calculate loss and then how we update our weights and biases to make our prediction more correct and reduce our loss. So today we will be applying the gradient descent in a neural network architecture. So first of all, what is neural network? So this diagram here, as you can see, this is a neural network. It has multiple nodes and each node is connected to every other node in the subsequent layer, and there are multiple layers. The starting layer is called input layer, the last layer is called the output layer, and all the in between layers, there can be how many as you want, is called the hidden layer. So as you can see, the input layer is connected with the hidden layer by these arrows, and each arrow has some weight, say W11, W12, and each node has a bias. So when you propagate this input, say I1, to the next layer, what you do is I1 into W11 plus B1, and similarly I1 into W12 this arrow plus B2. Similarly for I2, I2 into W21 plus B1, I2 into W22 plus B2, and similarly you move more forward, and this part where you are taking the input, you are moving forward in the network, and you are getting to the output. This is called forward propagation. This After this forward propagation, we calculate the loss. We are using MSE or mean squared error for calculating the loss, as told in the previous video. So therefore, loss is y actual minus y predicted whole square, and our gradient, that is dl by dy bar, is equals to y predicted minus y, because if you differentiate it, it will come 1 by 2 y bar minus y. The 2 we can ignore as it is a constant. Then I have written y dash, as you can see. I will zoom in. This y dash is the forward pass equation of this neural network. You can follow that I1 into W11 plus I2 into W12 plus B1. So this one plus this arrow plus B1 whole multiplied with W3. I will explain where the W3 came from. Plus you understood where this first bracket thing, this part came from, right? This one. Next, where next we are using for this node, this B2 node, we are having I1 into W21 plus I2 into W22 plus B2. Now we are here in the first hidden layer. Now we propagate to the output layer. What we need to do, we need to multiply this layer's output with W3, as we are doing here, and we need to multiply this B2 node's output with W4, as we are doing here, and then add both of this with a constant term B3. As you can see through the arrows, O1 is the output of the first node and O2 is the output of the second node. So O1 into W3 plus O2 into W4 plus B3 is our final Y bar, or our Y predicted. Now what we need to do, especially in backpropagation, is we need to calculate that how much each of these weights and biases contributing to the loss, and accordingly we need to upgrade these weights and biases. So let's see how we can calculate first, how we can calculate how much these weights are contributing to the loss. So for calculating how much this weight is contributing to the loss, we need to differentiate the loss with respect to that particular weight. So let's say first of all we have the loss, we have the final loss, and now we want to find out how much W3 is contributing to this loss. So what we do is dl by W3. If you, I will suggest you to differentiate once, like this function is already written. You differentiate once in your own pen and paper, then you will understand it very well and you don't need to study it from anywhere else anymore. So as you can see, dl by dw3, we get what? This gradient. G is gradient into dy dash by dw3. So now what is this dy dash by dw3? Here I am saying it is O of 1 or the output. So now how is that output coming now? So the output it is coming, let's see, we need to do dy dash by dw3. This is our y dash equation. Now we see which term is multiplied by w3. This O1 term or the output 1 term is multiplied by w3. So when we differentiate y dash by w3, all the other terms except this term will become 0 and this term will stay. So dy dash by dw3 is nothing but actually O of 1. Now how, like every time we can't differentiate. If the network is very large, we can't find it by differentiation itself every time. So in other, like how else we can find it? So another way to finding is we can use matrix property and we can cleverly use matrix multiplication to find this out. So let's see how that is done. Let's say this is our O1 O2. Now how will we finding the O1 O2? Okay. O1 O2 is our previous layer output and this W3 W4 is our current wave. Now to upgrade those waves, first we need DL by DW3. This is sorry, this is actually DL by DW4. To calculate our output, our new weights or our upgraded weights, so first of all we need what we have here. We have our old weights W3 and W4 minus our learning rate multiplied with our gradient, that is G, multiplied with our previous layer output, that is O1 and O2. Now this is a generalized formula. So when you need to find out the how much this weight has effect on this loss, what you can do is weights minus, like this part, this last part is the how much this weight has effect on this loss, and this is the upgradation. So weights minus learning rate into gradient matrix multiplied with previous layer output transpose. So O1 O2 is majorly present in this single column matrix. We transpose this to single row matrix. Secondly, after we upgraded the weights, again I will say one. First we have the weights W3. We find out how much W3 has an effect on loss by doing dl by dw3 or finding the differentiation of loss with respect to W3. And we find out it is actually G1 into O1. Similarly, we do the same for W4 and we find out it is G into O2. Now, to get the generalized formula, what we are doing, G into the output of the previous layer. Similarly, now we need to update the biases, B3. Now, similarly, what we need to do, we need to find the differentiation of the loss with respect to the bias to find out how much this bias has an effect on this loss. So as you can see, dl by db3, if you do it here, then you will find b3 is the only single term here and therefore it is a constant. Therefore, the total dl by db3 is g, because g into y dash when you do, then you get the differentiation of loss with respect to the bias term. Next, what will be our new b3 new? So our b3 new will be nothing but simply b3 minus learning rate into gradient. Learning rate is important, as I have explained in the previous video. Gradient gives us the negative of the direction we need to move to minimize our loss. So we are multiplying gradient, the direction the negative of the direction we need to go to, into the step size or the learning rate, and we are uh, subtracting it because the gradient is actually the opposite direction we need to move to now. So when we subtract it, we move in the right direction. Okay, so till now what we have done, we have propagated and we have find out the weight, how much this W3 and W4 has a part in the loss, and we have updated W3 and W4. Next, we have found how much B3 has a part in the loss and we have upgraded B3. Now, next what we need to do, we need to like, okay, think it like this. You have found the loss for W3 and W4. Now you need to find out the loss for W11, W12, W21, W22 similarly, right? So let's find out what is the differentiation with respect to W11. So if you, like I told, you keep a pen and paper ready. If you differentiate y dash with W11, what you get is this part I1 into W3 and I1 into W4. That is what written here. So what you get dl by dw11 equals to g into I1 into W3 plus I1 into W4. Now how can we get that? As this is our generalized formula. This is our generalized formula for getting the upgradation of the weight. So same I have used here as well. I have first written all the weights W11, W21, W21, W22. Then I have written the learning rate minus learning rate into gradient mu into I1 by I2. I1, I2. Now what is this gradient mu? Why can't we use a similar gradient? Because what was our first gradient? See, our first gradient was G. So if you multiply this with G, the learning rate is constant. So if you multiply simply with G, you won't get this equation. So to get this equation, what we need to do is we need to upgrade our gradient by how much? Now our new gradient should be gradient into next layer weights, or if you are calculating for this hidden layer, what is the next layer? The output layer. So gradient into the output layer weights transpose. Now you see this is our new gradient. Let's say G into W3 W4. Now if we write here this equation, if we calculate little more, what we will get is, let's say this is our so let's say we are doing our G mu is G into W3 W4. Now we have this here. Let's copy this one. We have this here. Then we have our learning rate as well. Only thing we are upgrading is our G mu. So only thing we need to upgrade here is this G new part, and this is actually G in or we can say this is actually G into W1 sorry G into W3 comma G into W4, and this will be our new gradient. Now if you multiply and see this one, if you multiply and see this one, huh. Now if you see this one, this gradient is here and you are multiplying it with the output itself, and what you are getting is this equation. So this equation what it gives is, it helps us upgrade our weights in the hidden layer. So why do we change the gradient? We are changing the gradient so that this equation fits in well with this generalized equation that we derived in the previous in the output layer. Now what we have done, we have updated our weights, updated our biases, and also updated our gradient, so we can do the same in the next layer. Now third, one of the more important topics in neural networks is activation layer. Now what is the activation layer? So in between layers there is linearity, and to break the linearity or to get a specific type of property from the layer output, we use activation layer. So say in this, when the output is coming, this output is coming through another small node, and what this node is actually nothing but ReLU. So I am writing ReLU here only, and I'm not giving the small node here, but for your understanding, you understood that this output is coming into this node, then propagating forward. So what this ReLU layer does is, it gets a x value, their x value, and gives a specific y value in return. So if the x value is less than 0, then the ReLU returns y value 0 or a constant, say this is some constant here, say k. So if the x value is less than 0, then the ReLU returns us k, and the x value is greater than 0, somewhere here, then the ReLU will return us some linear equation on the x value. Maybe it's directly the x value, or maybe some constant multiplied with the x value. So this is the ReLU layer. It takes the function, takes the input, and gives the output according to this curve. So now this ReLU layer also we need to, like when we are moving through this, before going to this node, we need to take our gradient through the ReLU layer also. Na? So that is very easy. The differentiation of ReLU layer if the x is less than 0 is 0 because the slope is 0. And the differentiation of the ReLU layer if the x is greater than 0 is 1, as you can see. So now this diagram will clearly explain the flow of the gradient across this neural network. First we have the loss, then we have the output gradient that we are calculating. Now this output gradient, two things we are calculating. One is L1 output transpose, or the output of the previous layer transform multiplied with the output gradient. That is our change in weights we need to do. And this directly output gradient, this is our change in biases. Okay. Second, we are propagating this output gradient to the next layer or to the previous layer. So what we need to do is multiply the output gradient with the weights transposed, as we have done here while upgrading the gradient. Weight transpose, this one we are doing in this box. Then we are propagating it through the ReLU layer. That 0 if it is 0, less than 0 or 0, and a constant 1 if it is greater than 0. So this ReLU layer, this gradient goes through the ReLU layer by differentiating. Then next we again calculate the weights of the hidden layer by doing input into layer 1 output gradient, and layer 1 output gradient is the bias, like the bias, how much bias we need to increase that. So now if this is clear, it will get more clear when we practically apply this. I will show you how to write a neural network from scratch using Python, NumPy and Pandas. So let's go. Now as you can see, we are in our Jupyter notebook environment. First of all, we will import all the required classes. Let's run this. These two are not required here, I think, but let's leave it there for now. Now, next we will be using the same dataset as in the previous video. I will explain one. This gives the weather, the maximum weather of that day, the minimum weather of that day, the rain percentage or the rain probability of that day, and the next day's maximum weather we need to predict using these three. And the date is arbitrary. So we will load this dataset from our weather.csv. Don't worry, everything will be provided in the description. Now, which of these columns are our prediction columns, or which of these columns we will put into our neural network? That is T max, T min, and the rain probability that day. These three. Next, what we will be calculating is our T max tomorrow, or tomorrow's temperature. So we will split the dataset into train, validation, and test datasets. Let's do that. Next up, we will initialize the parameters of our neural network. So for every layer, given layer, let me show you what layer is actually. This is actually how many nodes there are present in this layer. Like 3 nodes are present in the input layer, then 10 hidden layers, 2 hidden layers, then 1 node is present in the output layer. That is our Tmax tomorrow. So first of all, we will initialize the weights and the biases. So in this param list, we will create a blank param list, and for each I in the layer, like total number of layers present, we will see weights equals to np dot random. We will make a random matrix of the weights, and what is the size of that matrix? That is layer I minus 1, that is number of nodes in the previous layer, is the number of rows, and layer I is the number of nodes in the current layer, is the number of columns. This divided by 5 and zero point 0.5 is used to put it into a range of 0.2, like minus 0.2 to plus 0.2, because random gives us values between 0 and 1. So we are putting into a different range for better calculation. Next, bias is np dot ones, and the size of the bias is straightforward. The number of nodes in that current present layer. If you see the diagram once, the number of weights there are, see, if you see here, number of weights here are 2 into 2 4 for this hidden layer. So number of rows in the previous, and the number of nodes in the previous layer is the number of rows, that is 2, and number of nodes in the current layer is the number of columns, that is 2. So 2 cross 2 matrix is my weight matrix, and there are two biases, B1 and B2, that is equals to number of nodes present in the current layer. So that we are initializing it, then we are pushing it into this empty list in a dictionary with weights and biases, and then we are returning our parameters. Okay. Now next we have our forward pass or our forward propagation. So what we are doing first is we are saving our current batch or the current input first we are saving into this hidden layer, hidden list. Now for every for in the range of the length of the layer, what we are doing is we are multiplying the batch with batch into the weights of that layer plus the biases of that layer. So easy, this is very easy. We are taking the input, multiplying it with the weights. We are doing matrix multiplication because if it is 1, then we can directly multiply, but if it is a batch of inputs, then we need to do matrix multiplication. And then we are adding it with the biases. Now next up, what we have is this. So what is this? This is actually the ReLU. If you see closely, what we are doing here is we are taking maximum of 0 or the batch. So what is happening is if the x value is less than 0, then we are returning 0. But if the x value is greater than 0, then we are returning the x value itself. So this is introducing the ReLU layer in our neural network. What it does is it helps in like making it more non-linear, making the neural network non-linear. Now next up, after calculating the batch, we are pushing it into our hidden list. For this hidden list will come into use in backpropagation. I will show you where. Then we are returning our output in form of batch and our hidden list. So next, this is our mean squared error, as you also seen in the previous video. This is our mean squared error, actual minus predicted whole square, and this is our gradient, mean square gradient, that is predicted minus actual. Next up is the main part, and that is the backpropagation. So we will understand properly what is backpropagation. Okay. So first we are passing the gradient, the parameters, the hidden list, and the learning rate. The gradient, the parameters, the weights and biases parameters, the hidden list or all the inputs and outputs that we stored in the hidden list in the forward pass, and the learning rate. So what is happening here is we are looping through from I to the range of the length of parameters or the number of layers in reverse. So we are going like if there are three layers, we are going uh, 3, 2, 1 like that, like in reverse. Now, if I is less than length, like while applying ReLU, we apply to only those to all the layers except the output layer. So here also, while calculating the gradient, we are applying the reverse ReLU or the differentiation that I told you. How is that done? NP dot multiply, that is NumPy dot multiply the gradient into NP dot heavy side. What heavy side does is, if 0 is greater than it returns 0, and like this actually does the differentiation of the ReLU layer with NP dot heavy side. So for every x, we are finding the differentiation and we are multiplying it with the gradient to upgrade the gradient according to the ReLU layer. So for all the layers that except the output layer, we are applying the ReLU, like we are applying the reverse ReLU or pulling our gradient through the ReLU layer. Next up, we are just doing gradient equals to transpose of gradient for the help of multiplication. Or else, if you write and see once, as I told, keep a pen and paper ready. If you write and see, you can't multiply the gradient directly because the number of columns in the first matrix and the number of rows in the second matrix should match for matrix multiplication. So for that, we are transposing our gradients. So now, if you see this diagram here, then as you can see, first we have the loss, then we have the output gradient. This first step is done for us. Next, we need to calculate the change in weight or the weight gradient. So how can we do that? Output of the previous layer multiplied with our gradient. So let's do that. Let's see what is happening here. Gradient into hidden I. Hidden I. Now here is where hidden comes into place. We were storing the values in the hidden list for this moment. Like we can use that layer like output to multiply like the previous layer output to multiply with the gradient, and hence we will find out the weight gradient or how much each weight is contributing to the loss. Next, we are calculating the biases gradient. That is pretty easy. That is just mean of all the gradients, or as I have shown here, the bias gradient is just the gradient. So if you have multiple gradients for a batch, say you are taking 8 inputs at a time, then you will get 8 gradients. So you are taking mean of all those 8 gradients. After that, what we are doing here is we are upgrading our gradient for the next layer. So params I or the weights of that layer multiplied with gradient whole transpose. As you can see here, this one. Gradient into weights transpose, or because we have transposed our gradient previously only, we can directly multiply with the weight and then transpose the total thing. Next up, what we are doing, we are updating our weights and biases. How? This is the weights minus learning rate into our weights gradient plus 0.1 into params of I of weight, like the previous weight multiplied with 0.1. Now why this 0.1 is coming here? So this 0.1 term is also known as L2 regularization. What this does is it stops the weight from overfitting by reducing a little from the weight before it actually upgrades. So if you want to know more about L2 regularization, I will make a separate video about it because it is a very big topic and video will get really long if I explain this now. But even if you don't have this term, for this small data set, this will work well. But if it's a bigger data set, this term is important. Now next up, we are upgrading our biases and at the end, we are returning our parameters. Okay, so this is our backpass or back propagation function. Now this is our main function. What we are doing? This is our layer structure. So we will have 3 inputs, 10 hidden layers, then again 10 hidden layers, and finally one output layer. And our learning rate will be 1 into 10 to the power minus 6. We will train the model for 10 epochs, or for the whole data we will train it 10 times on the whole data. Now what is batch size? Batch size is at a time, like before upgrading the gradient, at a time we will send 8 size batches, and for all those 8 size batches it will calculate the forward pass, then it will calculate the backward pass, and it will upgrade the weights accordingly. So first we will initialize our parameters. Next, for epoch in the range of epoch, so for from 0 to 10 or 0 to 9 here because the range. So epoch loss, we are initializing it to the 0 for every epoch. Then for I in range of 0, so from 0 to the length of train X, or the number of rows in train X, for every batch size, like 0 to 8, then 8 to 16, 16 to like that, with the step size is 8, because at a time we are taking 8 inputs and pushing into our model. That like 8 inputs parallelly we are pushing into our model actually. So first what we will do is we will get our X and Y by taking the first 8 inputs, then the second 8 inputs, like this we will take our X and Y. Then we will calculate our prediction and hidden after the forward pass. So we will get our prediction or batch, and we will also get the hidden list. That is the input and output of every layer. Next, what we will get is we will get our epoch loss. Sorry, we will upgrade our, or we will calculate our gradient using MSc grad. Then we will calculate our epoch loss. That is the np dot mean of gradient square, because gradient is differentiation of loss with respect to y, and if you do square again then you will get the loss. So epoch loss is np dot mean gradient, like We are for every batch we are calculating the loss and adding it to our total epoch loss. Then we will upgrade our parameters by back propagation. So we will pass all gradient, our parameters, the hidden list, and our learning rate to the backpass function, and we will upgrade our parameters. So this loop will continue until we exhaust our dataset. That is one for one epoch, and after every epoch, we will calculate our we will calculate our predictions, and we will see our validation loss. So what we will do is we will get the validation prediction by forward passing with validates and our upgraded param, and then we will print the epoch, the total epoch loss, and the validation loss by doing MSC valid y and our predicted divided by the length. So let us run this. It won't take much time. As you can see, already done. So our epoch loss at this stage, like at the last stage, we are getting 9.8251. As you can see, slowly the epoch loss decreased, and after that it became a constant, like almost became constant. And our validation loss is 0.01. That is very good. The model is trained well, and it is very good. Now we will calculate our test loss. Similarly, test loss we will initialize with 0. We will get the test prediction by doing a forward pass in the model. Then we will add the total loss or mean squared error to our test loss, and we will showcase it dividing with the length or like normalizing it. So we get a test loss of 0.11. So good, it is close to the validation loss. That means our model is not overfitting. Okay. If the if the loss you are getting while training is low, and your test loss is very high, that means your model overfitted a lot to your training data. But as you can see, our test loss and validation loss and our training loss is same. So that means our model is generalized, and that is a good sign. So last we will make one prediction. So we will like this n equals to 0 is which index we need to predict. So we will take the prediction by doing a forward pass at the n index for the test set, and we will pass in our final parameters params, and we will print our prediction. So let's see. As you can see, it predicted 97.62. That is our next day's temperature, and actually 968, 67.62 and 68. So good only. Okay, let us predict for some other value of n. As you can see, 73 is the actual temperature, and our predicted 83 is the actual, and our predicted is 73.7 or close to 74. So okay, this one is not that good of a prediction. Let's see another one, say n equals to 5. As you can see, actual temperature is 65 and our predicted is 67. So 2 degrees apart. This one is good. So similarly, you can try with different length of like this input and output will be same for every neural network. Not every, like in this data set, every neural network. So 3 inputs we are giving, 1 output we are expecting. Inside you can tweak with this values of the hidden layers, and you can get this, like see what other results come. So that is it for today. So today we saw a neural network from scratch using NumPy and Pandas. Please consider subscribing and liking and sharing. And in the next, we will be seeing neural network for classification task. Thank you.